Okay, in this video, we're going to start chapter 2 of the algebra textbook. Chapter 2 is on functions and relations. In the previous video, I gave an overview of what we're trying to learn in chapter 2 and even in upcoming chapters. And so one of the main things that we're trying to learn as we go forward in algebra is that the majority of equations or expressions or inequalities that will use to model something in real life, whether it be engineering, business, biology, chemistry, etc., the majority are going to contain more than one variable. And so one thing we want to learn how to do is we want to be able to analyze relationships between different variables in equations or inequalities or expressions. Because let's say I've got a linear equation in two variables like this. Well, I can pick an x and solve for y, or pick a y and solve for x. But if I change x, that's going to change y and vice versa. So there's a relationship between these variables. And you can look at any equation or inequality with any number of variables as long as it's more than one variable, and you can think about how all of those variables are related. And so we want to be able to analyze these relations. Because like in practice, the variable x and the variable y is going to have some real meaning. So it's very valuable to understand how exactly they're related. Okay, and one of the techniques that we use to do this is with graphs. So primarily it's going to be a graph in two dimensions, so in a plane, like the plane of your computer screen, or a graph in three dimensions. And so how can a graph help us to analyze relationships between variables in equations? Well, okay, let's take a look at section 2.1. Okay, so, well, first of all, what exactly is a graph? The definition of a graph is that it's a diagram that shows the relationship between variable quantities. Okay, and it does this using a coordinate system. And so now if we don't take this slow and get some of these terms really clear, it can become really confusing as you get into physics and engineering and vectors, etc. So, okay, let's kind of break this down from the ground up here. First of all, a coordinate system. Let's make sure you understand exactly what a coordinate system is. Fundamentally, a coordinate system has nothing to do with algebra or math. Okay, a coordinate system is used to locate actual physical points in either 2D or 3D space or even like 1D space on a line. Okay, so the literal meaning of a coordinate system, the true meaning of it is, so we live in a 3D world around us. Okay, we live in 3D space. Okay, so here's 3D space. A coordinate system is just you walk outside of your house and pick a point that you want to put an origin at. So you're going to put an origin at that point. Then what you're going to do is you're going to make up some system that will allow you to map out any point in space around that origin. So someone could give you what you would call coordinates, and then you would say, okay, I know exactly what point you're talking about. You know, that's the bench at the other side of my backyard, or whatever, right? Now you can have a coordinate system in 1D if it's along a line, like maybe a racetrack, horses run along a line or something. You can have a coordinate system in 2D in a plane, or a coordinate system in 3D. And then anything more than that, we can't actually conceptualize outside of anything past 3 dimensions. Okay, that is the true meaning of coordinate system. Even though we're about to learn the rectangular coordinate system, the Cartesian coordinate system for plotting equations, etc., still remember that a coordinate system has nothing to do with inherently, like in terms of the fundamental meaning, it has nothing to do with math. Yes, we're going to plot equations in a coordinate system, but we're doing that as a visual aid because our eyes see space. Our eyes see flat surfaces. Our eyes see 3D space. So so any visual aid, it makes sense that we would use a coordinate system, which is used for actually in literally for mapping out points in space. We might use that as like a visual aid for other purposes. That's why you might get confused sometime, in a few years from now, and you're thinking, how could, like, if we plotted price on this axis and cost on this axis and expenses on this axis? Well, how can price have a direction? How can cost have a direction? It doesn't have an actual direction. It's all because we're using a coordinate system, which has nothing to do with math, as a visual aid for interpreting what equations, the inherent meaning of an equation and the relationship between variables. Okay, so it's really important to remember that. How can price go north? It can't go north. It's just that we're using a coordinate system as a tool in math. And we do that in a lot of subjects because we see, our eyes see space. Okay. Now, the next thing we want to be clear about is, so this term dimension, so like three-dimensional space, planes are two-dimensional, lines one dimension. What are we talking about there? What exactly does that mean, like dimension? I mean, yeah, like you could go into a wormhole and you go into another dimension, okay. But then, like, space is three-dimensional. So we can go into three different dimensions. What are we talking about? The term dimension, what that's referring to is that, so if you're a caveman, cavewoman, you go into the world and you walk outside, you just wake up, walk outside, and you see this world around you. But you're observing that there's different phenomena that you can think about trying to, like, measure, quantify the magnitude of it, like distances between points, distances between objects, how hot or cold something is, how loud something is, right? How heavy something is. There's different things you can think about trying to, like, quantify or measure. Okay, and so if one of the things you're trying to measure is distances between points in space, or like locations of points in space, which in essence comes down to, because you place an origin, it comes down to, like, if you're trying to map out this point and provide coordinates, you're really, if this has coordinates 3, 5, 9, you're really saying this is 3 units in one direction from the origin. This is 5 units in one direction from the origin. This is 9 units in one direction from the origin. So it's like, even with a coordinate system, you're specifying some distance from the origin. What's unique about space around us is that if we want to uniquely specify all points in space, if we're in some room or whatever, all these points around us, you have to have 3 separate quantities, 3 distinct quantities. You have to. There's no other way around it. As opposed to, like, something like time. Well, time is one-dimensional. You only need one number to specify, like, the time of something. Same thing with temperature. You just need one number. But space is unique. There is no way for you to create some coordinate system that maps out all these points around you with just one number. You can't do it. You have to give 3 separate parameters. No matter what kind of coordinate system you use, when it comes to all the space around us, you have to give 3 separate, they're completely separate parameters. You have to. That's why it's three-dimensional. That's the idea of these directions being, like, independent. Okay, and so how can we use a coordinate system as a visual aid to study the relationships between variables in equations? Well, what we can do is we can, instead of having, one unit in, let's say, we'll say this is X, Y, and Z. And so when you have a coordinate system, you specify whatever you want. Like, if this was an actual coordinate system in 3D space, you'd measure off, that's 1 inch, 2 inches, 3 inches, 4 inches, etc. You'd mark it off. However, depending on in whatever unit of distance you were using. Well, instead of the visual aid is going to be, instead of X, Y, and Z necessarily being actual distances in space, well, they could be a variable that's a placeholder for any kind of quantity. X could be the price of something, whatever. It's anything that we've been learning how to solve word problems. It's like you have a word problem or some problem in real life, and you make a model out of it, an algebraic model out of it, and there's multiple variables. Well, okay, in one of those variables could be X, whatever it means, and each of these marks is a unit in like a dollar or whatever you want it to be. You could mark it off however you want it to be, miles per hour, whatever. And then y could be the one of the other variables, and z could be one of the other variables, whatever. And then what you could do is you could think about how you could like pick an x-y pair, and you see where that point is. Like pick a value of x, pick a value of y, see where that point is, and then solve for z, because then you can have an equation in one variable. Solve for z, get z, and then go up or down in the z and plot that point. And you could do this for a lot of points. And then since like a variable, any variable x, y, and z is, technically it's an infinite number of values. This is any value along the real number line or whatever. You could just connect all the dots into like a smooth curve, and that would be a representation of the equation. And you could see visually how these variables in the equation are related, even though they're not necessarily related, have anything to do with actual 3D space. It's just a visual aid. And that's exactly what we're going to do. Okay, now, what you can think about is that as far as like the coordinate system, okay, so you go outside, you pick a point as the origin, but so if you're going to be in 3D space, you're going to need 3 separate parameters. If it's going to be just in a plane, you'll need 2 separate parameters. But you can come up with any kind of coordinate system you want. You can do whatever you want. There's all kinds of ideas. You're going to need 3 parameters, but the 3 parameters you need, you can make up anything you want. Okay, and so, but the most commonly used popular coordinate system in physics, science, engineering, and algebra is what's called the rectangular coordinate system, or also known as the Cartesian coordinate system. Okay, so let's come here. It says, mathematician René Descartes in the early 1600s was the first to identify points in a plane by a pair of coordinates. He did this by intersecting 2 perpendicular number lines with the point of intersection called the origin. These lines form a rectangular coordinate system, also known in his honor as a Cartesian coordinate system, or simply a coordinate plane. The horizontal line is called the x-axis, and the vertical line is called the y-axis. The x and y axes divide the plane into 4 quadrants. The quadrants are labeled counterclockwise as 1, 2, 3, and 4. So, okay, we're going to start in 2D instead of 3D. And so again, if you're going to think about making a coordinate system in a plane where you identify locations in space of all points, different points in a plane, well, you can do it any way you want, any way you can imagine. But again, as I mentioned, since a plane is 2-dimensional, it's going to require 2 parameters, no matter what, to specify the locations of any point in a plane. And what René Descartes did was he said, okay, well, we know we have a number line that contains all real numbers, right? This is like 1, 2, 3. Well, Descartes said, why don't so I've got this horizontal number line here. Why don't I put another number line that's vertical and passes through the 0 of the horizontal number line? And I'll call that point of intersection the origin. Okay, and now with these as what we'll call major axes, and we'll call this the x-axis and this the y-axis, now any point in this entire plane, like we're still thinking about location in space, can be identified. Any point in this entire plane. So the number lines extend infinitely in their respective directions, and that's what a plane is. A plane extends infinitely in all of its directions, but it's still 2-dimensional. Okay, and all we would need is a pair of values, which we call coordinates, to identify any point in this entire plane. Okay, so it says every point in the plane can be uniquely identified by using an ordered pair. So an ordered pair, x, y, an ordered pair. 2-dimensional, it's going to be an ordered pair. If it's 3-dimensional, it's going to be 3 numbers, with the first coordinate being called the x coordinate and the second called the y coordinate. And the idea is, so the origin is 0, 0, because you haven't moved any distance along in the positive or negative direction parallel to the x-axis or parallel to the y-axis, so you're at the origin, 0, 0. But then if you've got a non-zero number for x or y, that signifies how many of these major tick marks you've moved in the positive or negative, parallel to the positive or negative direction of the x-axis and the y-axis. So, for example, the point -3, 5. You go -3 in the x, and then you go 1, 2, 3, 4. You can't see the -5. It'd be somewhere down here. And that's what these minor axes are sometimes drawn in for. So you can, it's easier to kind of see. It's easier to see. I missed. I wasn't in line with -3, right? That's the point of the minor axes. So this would be somewhere in this region. This is -3, 5. Okay, and so this is let's do this. So okay, and it's called rectangular because everything, the essence of a rectangular coordinate system is that everything is perpendicular to everything. The major axes are perpendicular to each other. All the minor axes are perpendicular to each other. It's even the case if you go into 3D, right? Everything's perpendicular to everything. And you can draw out this point here, all of its minor axes, and it's rectangular. It's a rectangle, and in 3D you'll draw out this rectangular prism. Okay, and so what else? So this distance is called the x-coordinate, and this distance is called the y-coordinate. And you can see, because look, there's the amount you moved in the x, there's the amount you moved in the y, or here's the amount you moved in the y. That's like this is the x-coordinate, this is the y-coordinate. Okay, and so that's what you're doing with a coordinate system. You're plotting points. Even if we plot an equation is still just a lot of, you're plotting an equation. We're going to have these smooth lines, but that's just like a very large number of points you're plotting. A graph in a plane or in a 2D plane or a 3D region it's a bunch of points. You're plotting a bunch of points. Even if we've got an equation plotted like this, something like that, this is like an infinite number of points plotted. Okay, let's see what else. In the Cartesian plane, you can identify these different regions as quadrants. So this is quadrant 1, this is quadrant 2, this is quadrant 3, this is quadrant 4. Quadrant 1, both the x and y are positive. Quadrant 2, the x is negative, the y is positive. Quadrant 3, both the x and y are negative. Quadrant 4, the y is negative, the x is positive. And there's similar labels for, I think it's called octants. In 3D, you've got 1, 2, 3, 4, you have 8 octants, right? And again, if you look, I want to stress, even in any Cartesian coordinate system, rectangular coordinate system, 2D or 3D, everything is perpendicular to everything. You see, and if you plotted a point over here, then you can construct this like rectangular prism. You see? Okay. And yeah, so the most commonly used in all of physics, engineering, math, business, at least for non-math majors, is for doing graphs, is the Cartesian coordinate system in 2D or 3D. Now, it is important to note, though, that, and I'm going to talk about this more in the next video, but you can use any coordinate system you want. And you can graph points, you could graph equations with any coordinate system you want. So here's a polar coordinate system in a plane, but like in 3D, this would be cylindrical. But no matter, it's important to note, though, no matter what, the dimensions are going to be the same. So to map out all points in 2D space, no matter what kind of coordinate system you come up with, you're going to need 2 dimensions. So here, the dimensions, the ordered pair in this case is, I think it's theta r. Theta, or maybe it's r, what is it? Theta r or r theta? Or no, r theta. So all this is is so the theta is measured from the standard the position for like an angle, which is it's 0 at the positive horizontal axis, and then it goes from here. So it's theta is equal to 0 here, and then you go all the way around, and that's 0 to 360 or 0 to 2 pi. So, but the r is just the straight line distance from the origin in any direction. So you can see these major axes, like this would be 1 unit of radius, then 2, then 3, then 4, 5, 6. And then this is the different angles, pi over 6, pi over 4, all the way to 2 pi. So you can specify, like this point here would be, or let me do this. This point here would be, if you're mapping this out in 3D space, you've got an angle, or no, it starts with radius of 3 and a angle of 2 pi over 3. So that would be this point in space. And then, again, it's like you could have any kind of equation, y is equal to 2x plus 4, whatever. You could pick an x, solve for y. Pick a y, solve for x. Well, in this case, you could do this with a Cartesian coordinate system. Y is equal to 2x plus 4. Pick an x, solve for y. Pick a y, solve for x. Plot a bunch of points, and then you just connect those dots with like a smooth curve, because x is any real number. Like it could be, there's infinite number of between just 0 and 1, there's an infinite number of values, right? On the number line, 0.583, 1,000 zeros, 1. So that's the whole reason you're connecting the dots, because you're just accounting for, look, there's an infinite number of points technically I could plot this equation with. And so, but it's still just points though. And so you're picking an x, solving for y, picking a y, solving for x, and you plot it. You could plot it in a Cartesian plane. Or you could do the same thing. You could say theta is equal to, what was it? I forgot what I wrote, but okay. So theta is equal to 3r plus 4. Whatever, right? Pick an r, solve for theta. Pick a theta, solve for r, and plot it here. And then just connect the dots with a smooth curve. But it's going to look different because they're two different coordinate systems. Yes, there are ways where you could convert. Like if you had this is called, one of the reasons this is called linear, or I think it might be the main reason, is because something like this is called linear is because when you plot this in a Cartesian plane, or if you plot something linear in 3D, you're going to get a line. It's going to be a line. There's ways of, if you had this line in 3D space or 2D space, and you wanted to have this exact same line at the exact position, exact orientation, but in polar coordinates, there's ways we'll talk about this later, you can convert an equation from rectangular to polar so you get the exact same geometrical line. There's ways you can do that. But in general, if all you do is just say, okay, look, I started with y is equal to 3x plus 4, and now I'm just going to literally just swap out those variables with some other coordinate system, then no, in general, it's not going to be the same figure unless you like do a conversion. Okay, but I'm just saying you can use any coordinate system you want to map out points. Okay, and the cylindrical would just be the third. If it was cylindrical, the third coordinate would be z, r, theta, and z, which is like, it's just into or out of the page. So what you end up getting is this cylinder to map out all of 3D space. You do an r, a theta, and a z. Okay, the distance and midpoint formulas. What this is all about is they're going to give us a formula that allows us to calculate the distance between any 2 points in a Cartesian plane, as well as the midpoint between any 2 points. So like if you connected a line between 2 points and you wanted the coordinates of the midpoint, they're going to give us a formula for that. But it's for a Cartesian plane. But you could just as easily come up with a distance and midpoint formula for a polar plane. Now, what's the purpose of this? Like, why are we doing this? Well, okay, we're going to start to train, even though that like the fundamental meaning of a coordinate system is that you're mapping out points in 3D space. Well, we're going to be slowly transitioning to where we can abstractly think about these variables on these axes as being anything like price, cost, animals in a population, whatever, right? So yes, we're talking about distance. We're going to be using these terms that apply to space. But just remember, we're kind of abstractly extending these concepts to any kind of variable that you're working with: speed, money, whatever. Okay, so so we could have a Cartesian plane, and it might be useful to think about if you had like price on this axis, expenses on this axis, the idea of the distance between 2 points. Quote unquote distance. It's not an actual distance, but still, we're using this coordinate system as a aid to visualize these concepts, at least in 2D and 3D. So they're going to give us formulas that we use with coordinate systems, and two of those are based on the distance between 2 points, or the length of a line that connects 2 points, or the coordinates of the midpoints of a line that connects 2 points. But again, this is just going to be in our Cartesian plane. We could do this. We could find the exact same types of formulas for a polar plane if we wanted to. But we're focusing on the Cartesian plane. So, all right, it says, recall that the distance between 2 points A and B on a number line can be represented by the absolute value of A minus B, or the absolute value of B minus A. Yes. If you had 2 points on a number line, okay, the absolute value of X, or any number, is its distance from 0. But then we also looked at, okay, well, if we have 2 separate points, what's this distance? Just the magnitude of this distance. Well, you can use the absolute value there too. So, okay, this distance would be, it's equal to the absolute value of A minus B, or equivalently, the absolute value of B minus A. Okay, so it says, now we want to find the distance between 2 points in a coordinate plane. For example, consider the points 1, 5, and 4, 9. Okay, 1, 5, 4, 9. The distance D between the points is labeled here. Yeah, we want to find it's a magnitude, right? We want to find this distance, D. The dashed horizontal and vertical line segments form a right triangle with hypotenuse D. So, yeah, so you've got these 2 points here. And you can draw these dashed lines, one parallel to the x-axis and one parallel to the y-axis, that connects the 2 points. You could do this with any 2 points in the no matter what they are in the Cartesian plane, unless it's, I guess, if it's vertical or horizontal, then you can't. Then in that case, then what would happen? If it was horizontal, y would be 0. If it was vertical, x would be 0. But still, that's fine. You can still think about the idea of connecting the 2 points with these with a line parallel to the x-axis and a line parallel to the y-axis. And what happens is what you get is a right triangle. That's what you form. But what's nice about this is that we've got with the coordinates of these points, and the fact that these sides of the right triangle are parallel to the x and y axes, we've got the information we need, if we got the coordinates of these 2 points, to find what the length of this side is and what the length of this side is. And so that's nice, because if we have 2 side lengths of a right triangle, then we can use the Pythagorean theorem to find the length of the hypotenuse, which is what we're looking for. Okay, so the horizontal distance between the points it says, this horizontal distance is the absolute value of you subtract the 2 x coordinates in whatever order you want. And same with the vertical distance. Just take the absolute value of the difference between the y coordinates of the 2 points in whatever order you want. And so they get the horizontal distance is 3, vertical distance is 4. Then they apply, if we come here, they apply the Pythagorean theorem and get the distance between the 2 points. Okay, so it says we can make this process generic by labeling the points. So point P, you say is x1, y1, point Q, x2, y2. And then, okay, the horizontal leg of the right triangle is x2, is the absolute value of x2 minus x1, or equivalently the absolute value of x1 minus x2. Same idea with the vertical leg. applying the Pythagorean theorem, we've got x2 minus x1 squared plus y2 minus y1 squared, but they drop the absolute value because we're squaring it, so it doesn't matter anyway. And then they take the principal square root of both sides, and there's the distance formula. And so the idea is what you're going to do if you want to find the distance between 2 points in a Cartesian plane. You're going to label one of those points as point 1 and the other point as point 2. It doesn't matter which one is point 1 or point 2. You're going to get the same answer no matter what. Just one is point 1, one is point 2. Therefore, point 1 has coordinates x1 and y1. Point 2 has coordinates x2 and y2. Then you're going to plug them into this distance formula here, where you do x2 minus x1 squared plus y2 minus y1 squared and take the principal square root of all of that. And you can see why it doesn't matter which point you pick as point 1 or point 2 because you're squaring the difference anyway, so the minus is going to go away. And that's it. That's the distance formula. And then just to show you, it's interesting to think about, but the distance formula in a polar plane would be d is equal to the distance between 2 points, the principal square root of r1 squared plus r2 squared minus 2r1 times r2 cosine of theta 1 minus theta 2. So, pretty cool. All right, so if we've got these 2 points in the Cartesian plane, what's the distance between them? So, the idea is you've got, you're in some plane here, and here's the x-axis, here's the y-axis. You put these tick marks, and you map out. So -5, you'd be somewhere over here, +1. And 7, 3, 4, 5, somewhere over here, -3. They're asking what's the straight line distance here? What's the length of this line here? All right. So this is easy. We just label any point as point 1 and point 2. The other one is point 2. It doesn't matter at all. I'll do this as point 1. This is point 2. Whatever. So what we do is the distance is going to be, we do x2 minus x1 squared, the principal square root of x2 minus x1 squared. But you can see you could even do x1 minus x2 and it wouldn't matter. But okay, x2 is -5 minus x1 squared plus y, x2 is -5 minus x1 is +7 squared plus, and then y2 is 1, but okay, minus y1. This is really important. This is one of the skills in algebra that if you do this correctly, this is one of the skills you need to do well, learn how to do well. So we're substituting -3 here for y1. So it's minus y2 minus, and then what is y1? Y1 is -3. You see? So what we've got is -5 minus 7 is -12. And then here we've got 1 minus -3. That's 1 plus 3. You see? Okay, so we've got the -12 squared is 144. 4 squared is 16. Okay, this is 160. So 160 is 80 times 2. That's 40 times 2 times 2. That's 20 times 2 times 2 times 2. 10 times 2 times 2 times 2 times 2. 5 times 2 times 2 times 2 times 2 times 2. So, okay, 2 to the 4th divided by the index of 2 is 2 squared. So that's 4. And then we're left with 5 times 2. So that's the distance between the 2 points. Okay. So now determining if 3 points form the vertices of a right triangle. So yeah, all they're going to do here is find the distance between these 3 points in the Cartesian plane and then apply the Pythagorean theorem to those, like the largest of those three distances is going to have to be the hypotenuse if it's a right triangle. Then they just they take the sum of the squares of the two shorter distances, which would be the legs, and see if that equals the square of the longer distance. All right. Now, what other kinds of formulas can we use with a Cartesian plane? Or any plane, but we're focusing on the Cartesian plane. So we can also think about finding the midpoint, the coordinates of the midpoint between 2 points. So the line that connects 2 points, what are the coordinates of the midpoint of that line? So, okay, now suppose we want to find the midpoint of the line segment between the distinct points x1, y1, and x2, y2. The midpoint of a line segment is the point equidistant, from the endpoints. That means like these two distances are the same. If you remember from geometry, these two distances are the same. Okay, the x-coordinate of the midpoint is the average of the x-coordinates from the endpoints. Likewise, the y-coordinate of the midpoint is the average of the y-coordinates from the endpoints. So, it's all you're gonna need to do is say, take the you want to take the x. So you go this distance in the x direction. To go from one point to the next, you go this distance in the x direction and this distance in the y direction. You just want to find the average. So you're really taking you just want to find this. You're trying to find this midpoint and this midpoint. At least in terms of coordinates, you're trying to take half the distance between this x coordinate between the 2 points and half the distance between this y coordinate, and that's going to be, now you're going to be lined up with the midpoint. And so how do you do that? Well, what you do is if you just take this x coordinate, not an absolute value or anything, if you just take this x coordinate, add it to this x coordinate and divide by 2, it's going to give you this x coordinate. And since you're just adding, the order doesn't matter. With subtraction it would, but we're just adding. And same here. So all you have to do is just pick. The order doesn't matter. Like you could say, you could do x1 plus x2 divided by 2, that's the x coordinate, or x2 plus x1 divided by 2, that's the x coordinate of the midpoint. Then you could, the y coordinate, you could do y1 plus y2 divided by 2, or y2 plus y1 divided by 2, that's the y coordinate. The order doesn't matter. And again, what you're going to get is this coordinate and this coordinate, and that's it. We can see that's the x coordinate we're looking for, x midpoint, and that's the y coordinate we're looking for. You're gonna get this coordinate in you're gonna get the x coordinate of this point and the y coordinate of this point. Let me rephrase that. You're not going to get the coordinates of these 2 points. You're going to get the x coordinate of this 2 point and of this point and the y coordinate of this point, which is what you're looking for. Okay, so here's an example. If there is a line segment between these 2 points here, then what's the coordinate of the midpoint? Just add up 4.2 and minus 2.8 and divide by 2. That's the x coordinate of the midpoint. Add up minus 4 and 3, divide by 2. That's the y coordinate of the midpoint. That's it. Okay, so now we officially talk about how the main purpose of what we're doing here with these coordinate system is we want to use them to graph equations. And so I've already talked about this, but here they're going to go through it more officially. And so the relationship between two variables can often be expressed on a graph or expressed algebraically as an equation, right? So the relationship between two variables, you can still relate two variables with just a list of points. There's applications in real life where you can think about, I've got 5 or 6 points I can plot, or 10 points I can plot. Sure. But another way is that you have like an equation. Y is equal to 3x plus 2, or 5, whatever. Right? And then in that case, you pick an x, solve for y. Pick a y, solve for x, and you can get 100 points or more. But since x can be any real number on the number line, and same with y, there's really an infinite number of points that this equation corresponds to, right? Y or x can be between 0 and 1. There's an infinite number of points, 0.58325. It's infinite. So that's the whole reason with equations. We end up we plot a bunch of points and then connect the dots, and that's the graph of an equation. It says, okay, suppose that x and y are related such that y is 2 more than x. Y is 2 more than x. Okay, so now they plot this equation graphically in a Cartesian plane by like I just described. But another thing to note, though, about this graph is that every point on this line is a solution to the equation, right? That's important to note. Every single point on this line is a solution. Because what are you doing? You're picking an x, solving for y. That's what that means is that if you plug that x value in and you plug that, if you come to any point on this line here, that's the graph of this equation. If you come to any xy point on this line, you can get the xy coordinates. And you plug that x value in, that y value in, it's gonna solve the equation. You can get the same value on the left and the same value on the right. Okay, so that's important to note as well. The graph of an equation; those are all solutions. Okay, and they show that here. They pick a few points and plug those xy pairs into the equation, and they're solutions. So the set of all solutions to an equation is called the solution set of the equation. The graph of all solutions to an equation is called the graph of the equation. So, yeah, you can, the graph of an equation, which you can't do, you can only do this with equations that have 2 or 3 variables. More than that, you can't really graph it, but you can represent, this is just a way of showing the solution set to an equation. You could do it graphically, or you could do it with variables. So it's like something like the set of all x x is a real number such that y is equal to x plus 2. That's the solutions to, well, this is already solved, but like you could think about if you had some jumble of stuff and there's numbers all over the place and you simplified it as much as possible and you got y is equal to x plus 2, right? Maybe this started off a lot more complicated. Then you'd say, okay, well, the solution to this complicated equation is this line here. That would be the idea. Here, it's like already solved. So now, one of the goals of this text is to identify families of equations and the characteristics of their graphs. As we proceed through the text, we develop tools to graph equations efficiently. For now, we present the point plotting method to graph the solution set of an equation. In example 4, we start by selecting several values of x and using the equation to calculate corresponding values of y. Then we plot the points to form a general outline of the curve. So yeah, one of the ways that we're going to be categorizing equations and expressions, etc., going forward, we've already talked about how we come up with certain categories, if it's polynomial, if it's quadratic, radical, etc. But some more categories are going to be that any type of equation that has, if they have like a very similar shaped graph, that's going to be in its own category. That's another way we're going to categorize equations. And you can see, like, so anything that's linear in 2D or 3D or whatever, if we plotted 3x plus 2y minus z is equal to 5 in 3D, that's a line. And that makes sense because this is linear, right? And just to point out, the reason you might say, well, why do we do these graphs if we can't even if we can't even pass 3D, we can't graph it? Because it's going to help us to understand the equations. You can still think about if I had 3x plus 5y is equal to 5z minus 7w plus p, well, that's still linear. And so this is like, you can kind of abstractly think about, well, this is a line in 5 dimensions. Okay, so now, but as it says, as we proceed through the text, we're going to develop tools and tricks to graph equations faster and more efficiently and just with intuitive tricks. But now, right now, we're just doing the point plotting method to get used to the fundamentals of what we're doing here. So like we just, here what they want to do is they're going to give us an equation and say, okay, pick an x, solve for y, pick another x, solve for y, pick a y, solve for x, get like 7 or 8 points, plot all the points, and then connect the dots. That's like the fundamental roots way you graph an equation. But again, we're not going to, as we proceed through the text, we're not going to always be doing it that way. So, okay, if you have y is equal to the absolute value of y minus the absolute value of x is equal to -1. Okay, well, they solve for y. You don't have to, but... And now they just start picking a bunch of x's. And then you're, what do you... Yeah, you'd rather pick x's so you don't have to solve an absolute value equation, right? But you could pick a y and solve for x if you wanted to. So they pick a bunch of x's, solve for y. They plot a bunch of points, and there's the graph. They connect the points. They connect these points with a... you probably want to plot this. You definitely want to plot when x is equal to 0, the crossover point, right? And so what's interesting is it makes sense that the point where x crosses over from positive to negative, which is at 0, it like bounces off of that and goes back up, and that makes sense. With an absolute value, you're going to have this bottoming out point where it just stops and just turns back positive, and that's what you get here. Okay, the graph of an equation in the variables x and y represents a relationship between a real number x and a corresponding real number y. So yeah, at the moment we're going to focus on, when it comes to graphs, we're going to be dealing with real numbers. Yes, when we get to complex analysis, we can think about, okay, if we had complex numbers and we wanted to graph that with real numbers, how would we do it? But that's going to be beyond the scope of this course. Anytime we're doing a graph, it's going to be strictly involving real relationships between real numbers. Okay, so therefore the values of x must be chosen so that when substituted into the equation, they produce a real number for y. Yeah, otherwise you can't plot it. If you've got an equation with two variables, it needs to be the case that you plug a value of x in and you get a real number for x in, and you get a real number for y, and vice versa. Sometimes the values of x must be restricted to produce real numbers for y. Yeah, so if you have y squared minus 1 is equal to x, I mean, you could just leave it like this and just start picking a bunch of y values and solving for x, and you get a bunch of points, and that'd be fine. But they just want to give you some more perspective, and they want to think about, okay, well, what if you were picking x's and solving for y? What would you do then? Well, okay, in that case, you'd have adding 1 to both sides, square root property. Okay, well, the only thing here is that x can't be less than -1. If we're gonna be trying to graph this, and we can only work with real number coordinates, well, x can't be less than -1. It could be equal to -1, that's fine, but not less than -1. Now, if we would have just stuck with this equation and just picked a bunch of values of y and solved for x, that restriction would have been kind of like naturally applied anyway for us. But like we would have gotten this graph anyway. But it's just interesting to look at it from this perspective. What if I wanted to pick an x and solve for y? Well, you'd have to plug it in here. In this case, you couldn't be picking values of x that are less than -1. And that's what they do. They plot a bunch of points and connect the dots, and they get this graph. That's the graph of this equation here. These are all solutions to this equation. Okay, now x and y intercepts. When analyzing graphs, we want to examine their most important features. So yeah, that's going to be the idea. What we're going to be doing is we're going to be studying different types of equations. And one of the ways we're going to study the equation is through their graph, right? We're going to study the graph. And what we're going to be doing is, and that's going to help us to understand the equation. Like an equation like y squared minus 1 has a graph that looks like this. Well, what other types of equations have a similar looking graph? But more than that, what are some of the key features of this graph, and how does that relate to like the mechanics of the equation? If we use this to model something in real life, what do these different features mean? Okay, but first of all, what kind of different features are we looking for? Well, one of the main features of a graph is going to be where the graph intercepts the major axes, and in this case, with the Cartesian plane or any Cartesian 3D plane, 3D coordinate system, whatever, it's where it's intercepting the x, y, and z axes. So you could think about it even in 3D. In 3D, you're going to have like a whole surface. You'll have like these whole, you could have a whole surface in 3D. You could have like a sphere, right? but you can think about where does the graph intercept? Where does it cross over the x-axis or the y-axis or the z-axis? But in a Cartesian plane, if we look here, like, okay, look, it crosses the x-axis here. It crosses the y-axis at these 2 points. That's what x-intercept means and y-intercept means. Where does it intercept the x-axis? Where does it intercept the y-axis? So this graph here, it intercepts the y-axis at this point. That's a y-intercept. It intercepts the x-axis here. That's a x-intercept. So it's going to be useful if you have an equation. One thing you can do is, if you want to analyze that equation, find its x and y intercepts. And again, I want to stress, you could extend this to more than 3 dimensions. You can abstractly think about, okay, 3x plus 2y is equal to 5z minus w. Well, you could think about the x-intercept, y-intercept, z-intercept, or the w-intercept. Even though we can't visually look at something in 4 dimensions, you can still abstractly extend this to 4 dimensions, these concepts. So how do you solve for an x-intercept or a y-intercept or any kind of intercept? Well, in 2D, just thinking about this in 2D, what you're going to want to do is let's come to 3D. I think this would be even more intuitive if we just look at this in 3D. What you're wanting to do is, when you are on the x-axis, if you're on the x-axis, anywhere on the x-axis, so meaning it's an x-intercept, what's the case in that scenario? Well, no matter where you are, z is 0 and y is 0. If you're on the y-axis, no matter where you are, x is 0 and z is 0, and same with the z-axis. And you can extend that to any number of dimensions. If you want to find the w-axis intercept, in that case, the x-coordinate is going to be 0, the y-coordinate is going to be 0, and the z-coordinate is going to be 0. So you can set all of the other variables equal to 0 and then you're left with an equation in one variable. Solve that equation, whatever type of equation it is, and you've got the intercept of that variable. That's the idea. Okay, so now just here they outline this, what we just talked about for determining the x and y intercepts in a plane, Cartesian plane, but you could extend this to any Cartesian coordinate system in any number of dimensions. Yeah, just note that the idea of this idea of an intercept is where you just set everything else equal to 0 and solve for the remaining variable. We're only talking about a Cartesian coordinate system. When it comes to not like a polar coordinate systems or cylindrical, it's going to be similar, but it's not exactly the same necessarily. So the idea of what we're talking about right now, where if you want to find where a graph intercepts the x and the y or any axes in any Cartesian coordinate system with any number of variables, where you set all of the other variables equal to 0 and solve for the intercept you're looking for, that process is we're strictly talking about a Cartesian coordinate system. Okay, so if you have y is equal to the absolute value of x minus 1, find the x-intercepts. Okay, well, we set y equal to 0. The absolute value of x is equal to 1. Well, this is going to be 1 or minus 1. And if we look at the graph, that makes sense. 1 or minus 1, look, it crosses the x-axis. What about the y-intercepts? Well, you just set x equal to 0. There's one y-intercept. There it is. Okay, and so now this last section just talks about how what we're going to do going forward is we just looked at graphing equations with the point plotting method, and it's useful to do that at the start just to get a sense for the pure fundamentals of what graphing is. But obviously going forward, we're going to use more efficient techniques like graphing utilities, your calculator or Desmos, etc. Okay. Now let's work some example problems.